Let's rewind time to 1986. You may have heard of this nifty programming language called C that was developed for Unix operating systems in the early 1970s. Since then, the language has become more popular than ever. Some musicians are even quoted saying that the programming language was just like the B language, but one better, giving it a solid 11 out of 10. Abacus Super-C provides you with everything you need to learn this up-and-coming programming language on your C64 today. Who knows what the future of C will be like, but I have a good feeling it's going to be around for a while. For this video, I'm using a Commodore 64 with two 1541 disk drives. Everything shown in this video is available on the GitHub link in the description of this YouTube video. Abacus Super-C comes on one disk, and normally you'd put the disk in drive 8 and fire it up, but actually we're going to put it in drive 9 and start it up. Yep, the second drive. As we go through the product, you'll see why this makes using Super-C so much easier than having it in drive 8. So to get started, we're just going to type load star, comma 9, comma 1. You're immediately dropped into what is called the CCP. This is the C command processor. The CCP is a very lightweight shell, similar to like CPM or DOS. If you don't know what those are, don't worry. You don't have to have knowledge of either of those to use this. Right now you see a yellow B colon followed by a blinking cursor. This lets us know what the current drive is set to. In this case, it's B. Disk drives in Super-C are lettered A through H, allowing us up to 8 drives. Drive A is Commodore Drive 8, Drive B is Commodore Drive 9, etc. There are about 6 commands that are built into this CCP program, and they are known as resident commands because they reside in memory. There are other commands called transient commands that are programs on a disk. So let's take a look and see what's on a disk by typing dir. So the disk is divided into 4 sections of programs. First item is C-system. That's what we booted into to get this environment up and running. The next set of programs that are PRG files are what's called the transient programs. These are programs that can be launched and run within the CCP, the environment we're in now. And these programs are CE, the C editor, that is the full screen editor that we'll use to edit our source code. CC is the C compiler. This is what we're going to use to compile our source code into what's called object link files. CL is the C linker, and this will link object link files together into an executable program. We have the program copy. This is a single file copier. There's a program called device that's, in my opinion, kind of useless. It lets you change the device number of the drives on A or B. I'm not quite sure what the point of it is, but it is included on the disk. There's a program called F, and this is a fast loader, and it lets programs load faster. However, the programs that come on this disk have fast loading built in, so not quite sure what the point of it is, except maybe to fast load some of our own compiled code. C1 is a program that combines the C compiler and linker into one easy-to-call program, and type is a program that lets you view files on disk. The next set of files are called header files. These are files that are included in your C source code to link to external libraries, and we'll get into more of that in a little bit. The next set of files are the object link libraries that are the standard library of functions that are included in the package. Each one of these more or less equates to one of the header files. For example, STDIO.H is libc and libcs.l. Graphics.H belongs to libgraph, and math belongs to libmath. C-type actually does not have a corresponding object link file. And everything in the 4th section are source code to the demonstration programs that come with Super-C. And they are phenomenal to take a look at to get a handle of the capabilities and how to use certain aspects of the libraries and the C programming language. So we can use the dir command with other disks. And to do that, you put the letter of the disk that you want in front of the command. So we would type a:dir. This is going to run the dir command for the A drive. So we're going to press enter, and we will going to get an error. This is file not found. I don't have a disk in the drive. So one of the other resident commands that you can use is ERR, and this tells you the error of the last command it ran that caused the drive error. In this case, it's drive not ready. So we're going to insert a blank disk into drive 8, and because it's blank, we need to format it. This gives us another really useful resident command called com, C-O-M. And what you do is you put a space, and in here you type in the command that you would typically send to a disk drive in BASIC, the part that fits into one of those open 15,8, 15 commands. So this DOS command is to format a disk. N: means we're going to make a new disk. Hello World is the title, and CZ is the 2-letter identifier. So formatting this disk will take just a few moments. All right, if we type dir, and this counts for A:dir, so that it's going to do a directory against the A drive. And we'll see that we indeed now have a blank disk ready for us to fill with source code and programs. And there are 2 more resident commands I'd like to take a look at. TOD, and that displays you the time of day clock. Of course, it defaults to midnight, so at this point we're 5 past midnight. But we can set the time of day clock using the set command, and you would put in the same format for the time of day. So I'll put in, I don't know, noon. And now the time of day clock shows that it's noon, and you can see that it's moving forward. The time of day clock is kind of nice because when you're in the editor, it shows you the time of day while you're writing code. So this way, when you get really excited about a project, you don't spend the whole night working on it. All right, at this point, we're ready to work on our first program. So to get started to write a program, we need to bring up the C editor, the full screen editor. And we're going to do that by typing B:, because the editor is on our second disk, and we type in CE. So here we are in a full screen editor. And the first thing we'll notice is on the top right, our time of day clock is running. At the very top, we can see 2 numbers, 1 and 1. And that is the row and column that the cursor is in as we use the editor. And you'll see how the values move as I move the cursor around. Well, we need to start a new file because right now there's no file in the editor. As you can tell, next to the file prompt, it's blank. So we're going to press F5, and this brings us into what I call command mode, where we can enter command. And the commands are just single letters. So we're going to press N to start a new file. It's going to ask us how long we want each line of code. And you can put a value here between 40 and 80. To be honest with you, 80 is pretty much the only answer you want to put for this prompt. So we're going to type in 80 and press enter. And for our file, we're going to call it helloworld.c. When you're working with source code for C, you want to end them with a .c extension. This way you know clearly that this is source code for a C program. So we're going to press enter, and now we're in the editor. Now, you would think you could just start typing, and you'll notice that nothing actually happens. You just get this cryptic last line message at the top of the screen. When you start the editor, there are no lines in the file. And the very last line of the screen is a special line called the last line, and it's not actually a part of your source code. Now, in modern editors, you would think pressing enter might get you some lines into the editor, but that's not the case. You use the F7 key to insert a blank line. Now, I can type here, and if I move the cursor down, this is the last line. So if you want to add a whole bunch of lines, you press F7. And as you can imagine, F8 will delete lines. So let's start by writing our first function. C programs are just a collection of functions where when you run them, the function called main is run first. So we're going to create a main function, and we're going to write a program that just prints hello world to the screen. Something really simple and the most common first program that we ever write in a given language. So we're going to type in void main, open and close parentheses. So this tells us we have a function called main, and its return type, that's the type goes before the function name, is void. Void means it doesn't return anything. Now, in most languages, technically, there's no such thing as a function that doesn't return a value. Those would be called procedures. But we're just going to call these functions anyway. So this is a function that doesn't return anything. So now we need to designate where the block of code for this function goes. And you do that by creating a curly open and a curly close brace. Now you may notice on your Commodore 64 keyboard, there are no curly braces. That's right, the C64 does not have curly braces. So what do we do to get around this? The editor includes a custom character set that redefines Shift plus and Shift minus to be curly open and close. And as you can see from this beautiful hand-drawn picture that comes in the manual, they're above the plus and minus key. If you're on a real 64, you would just type in Shift plus and off you go. When you're in a Vice emulator, it's a little bit more tricky because you need to press like Shift plus, and you really can't do that. So the way you have to enter the curly open, if you're in Vice using the default keyboard layout, is you press caps lock, which puts shift lock on a Commodore, and then you press Shift plus, and that gives you a curly open. Before we continue on, turn off shift lock to put you back to normal. I'm going to press enter a couple times, then we're going to put shift lock back on to put a curly close. And to perform a curly close brace, you just press minus. and then we'll turn off shift lock. Now we want to indent our code, and you do that by pressing the back arrow key. That'll move the cursor to the next tab stop. Those asterisks along the dashed line at the top are called tab stops, and every time you press that back arrow key, it moves the cursor to the next one. We're going to start here at the first one. So we need to call a function to print some text on the screen, and we do that by using the printf function that comes with the C standard library. And what you do is you put the text in quotes that you want to print. So we'll put a quote here, and we're just going to type in hello world and a couple exclamation points. A quote, a close parenthesis, and a semicolon. Notice how as we approach the middle of the screen, it starts scrolling the screen horizontally. This is the way that they're able to easily give you 80-column editing, and it works pretty well. So here we press enter to move to the next line, and we'll press the back arrow to tab over to here. So once it displays hello world to the screen, there's another function we want to call that comes in the C standard library called getCar, and we're just going to call it like this. GetCar will wait for someone to type something on a keyboard, and it'll lock your program up until they press a key, and then it returns it. Well, we don't really care about the return at the moment. We just want to pause the program so we can see its output. So this is all we need. So at this point, our program will print the words hello world, it'll wait for a key press, and then it will end. But where are these functions coming from? How does the C compiler know that we're calling functions from the standard library? Well, you need to put in what's called a preprocessor directive at the top of your code. And we're going to use the number sign to do that. And you type in include space, and in quotes, you put the name of the header file. STDIO.H is the header file that declares the functions that are in the standard library, libc.l. If that's a bit much, don't worry, we'll explore more of it in a few minutes. But now we have a complete program. So kind of a neat feature of the editor is we can spruce up our text with color, right? So if we wanted to have, say, our preprocessor line appear in bright white, we can press Control 2 and it'll make it white using the color commands on your Commodore keyboard. We can also highlight blocks of code to do that. And we do that by pressing F5 to go into command mode, and you press C, and it's going to ask you what color number. So if we choose, say, 7, we'll press enter, and now using the cursor keys, we can highlight the block of lines we want to apply the color to. Then we just press enter, and it'll make those colors yellow. It didn't just delete the first line, by the way, it just moved us down a little bit. So now our code is a little bit more easier to read. At this point, we're ready to save our program and compile it. So to save this program to disk, we're going to press F5. It says again, enter command. We're going to use the S command to save it, and you can hear it saving it to disk. So next we're going to exit the editor by pressing F5 and X. I'm going to say sure. And now we're back at the Super-C command processor. So let's take a look at what's on a disk. So A:dir. And here we can see, very well by itself, the source code to our program. Notice how it's a USR extension. Not really sure why. You would think it would be a sequential file, but all their source code from the source editor is stored in USR files. So the next phase in getting our C program to run is compiling it. This is not going to create an executable program. This is going to look at our code and turn it into what's called an object link file, which is all the code in our source code compiled, ready to be linked with other libraries and other object files to create an executable. If you may recall, we included a file called STDIO.H. We need to put that on this disk in order for this code to compile. And that file is on the B drive. So on the B drive is that program called copy. So we put a B colon and we type copy to start copying a file. Now, if you put a file name like this, stdio.h, you think that would be enough. But anytime a file name is processed in its little shell, it's defaulted to drive 8 or letter A. So you always have to tell it what drive letter it's on if it's not on drive A. This is why we have this disk in drive 9. Because as you start working with lots of source code files, it'll drive you crazy trying to put inside your source code drive letters to everything. Then you put a space, and then we put the drive it's going to. So it's going to go to A colon, but that's not enough. It wants the file name. So you could type in stdio.h, and it'll copy it there. Or as a shortcut, you can put an asterisk, meaning just name it the same thing that we're reading from. Now, copy is a transient program. So first it has to load copy into memory, then it copies the file. Excellent, our file is now copied. So one minor annoying thing in a Super-C command processor is every so often commands will drop you to the drive you're performing the operation on. So even though we had B as the default drive originally, you'll notice that the dir command dropped it back to drive A. Now let's just make sure that our file is on a disk, and we'll type in dir. And there it is. We now have the two source code files we need to compile our program. We type b:/cc to start the C compiler. And again, that's going to load the C compiler off of the B drive. So at this point, the C compiler starts, and it's asking us for the source file name. This is the source code that we just created. So we're going to type in hello world.c. Now it wants to know what object link file are we going to create. And that's going to be hello world, and you'll notice that it added .o for us. Perfect. We'll press enter. This is asking us for a file name that it may create that will contain any kind of compilation errors, so we can look at them later. Error.e is a fine name. We'll just press enter. I do find it interesting how it put an A colon on that file name automatically, but not the two above it. Who knows? So first you'll see that it's working on hello world.c. It includes STDIO.H. It found source code for a function called getCharacter inside of STDIO.H, and we'll explore that more in a little bit. The hashtag means that it's done with STDIO.H. It then found our main function source code in hello world.c. It compiled it, and then hashtag means it ran into the end of hello world.c and a compilation is finished. And now it says there's a link file available. So this is a successful compilation. So let's press X to exit. And now we'll type in a:/dir to see what it looks like. And this is great. We now have code compiled. So now we want to create an executable program for us. And we have to do that by using the C linker. The C linker is going to take our object link file, the hello world.o, link it with a C standard library of compiled functions, that's libc.l, and produce a program that we can run. So we need to first copy that standard library to the disk so we can use it in the linker. So we're going to use the copy command on a B drive, and we're going to copy in libc.l, and we're going to copy it to the A drive. Okay, now we can type dir, and we'll see that we have hello world.o and libc.l. Those are the two object link files that we want to combine together into an executable by using the C linker. So now let's run the C linker, and we do that by typing b:/cl. This is going to start and launch the program that lets us link object link files together into an executable. So this program starts off by asking us the program file. This is going to be the name of the compiled executable, and we're going to call it simply hello world. So when it creates our program on a disk, it's going to be hello world of type PRG. So I'm going to press enter. Now it's asking us which object link files we want to include in this program. By default, it says libc.l, which is great because that's pretty much every program needs that. So we'll just press enter. Now it's asking us for a second link file. Well, we need our hello world.o object link file to be included in this program. Press enter. Now you can just keep adding more of them, but we only need these two, so we're going to press enter for this one. So what it's asking us is how much room do we want to leave for other things outside of our C program. So here's a memory map that's included in the manual, and it kind of describes where everything is when your C program runs. The one part that we care about at this moment is this third line, 0800 to CFFF. That is where our C program storage is. So what the memory top page is saying is what is the page number where your program is not? And it's kind of a strange way to put it, but D0 is the page number of D000, and our program exists from 800 to before that. So if you wanted your program to allow some space for maybe some machine language routines or maybe some data that you want to load directly into memory, you could lower this number to say something like C0, and then your program would actually end at BFFF. But we're going to leave it at the default for D0. That is just fine for probably 99% of the programs you're going to be writing with the C linker. So we're going to press enter. Now it's asking us a really interesting question. Would you like to create this program for the CCP or for BASIC? If you choose C, the CCP, which is a really good default while you're writing your code, it means that you can run the program in this environment and it can take command line parameters and do all the things you'd expect in a C program. If you choose B, which is what we're going to pick, this is going to create a program that anyone can run outside of this environment. So you can write your program and hand it to your friend and they can run it without having to have Abacus Super-C. So we're going to choose that option. The the linking has finished successfully. We're going to press X to quit. You could press R to restart and link another project, but I don't really feel that we need to do that. So we're just going to exit out. And now we're back at the Super-C command processor. And once again, we're going to take a quick look at what's on drive A. And there's our hello program. You'll notice that it's 36 blocks. It comprises of 21 blocks of the standard C library, 4 blocks of our hello world object link file, and then a whole bunch of overhead that is needed to have the C environment run. So it's a pretty big program just to print the words hello world on a screen, but there's a lot in there. So let's restart our computer and try it out. So if we were to load hello world, 8, which we will do, if we were to run this, it's going to fail the syntax error in 1985, which I kind of love the error number there. That's the year that I think they have released version 1 of this product. If we type in list, it's basically telling you, hey, you should have loaded this 8, 1. So we're going to replace this 8 with 8, 1. The nice part is you don't even have to type in run. It just takes over your computer with your program. Now this is very similar to what we saw when we loaded up the CCP. So as you can tell, it's loading the C environment. And here we go. So the C environment starts with a black border and a black screen and the default Commodore light blue text. All thing our program did was print hello world, and now it's waiting for a key press. When you press a key, it does a warm start and brings it back to basic. So there we've created our first C program and then we've run it. So let's continue our exploration of this product by jumping back into the CCP. And we'll do that with a load star, 9, 1. So let's explore the STDIO.H and take a look at what's inside of that and see how we're able to link from the source code to those object link libraries. So we can launch the C editor with CE, and you don't have to actually wait for it to load the file, and you can put the file name right here. And we're going to type in STDIO.H. This will load the version of standard IO.H on our source code disk. Because we didn't put a B colon in front of it, it will always default to the A drive. And here you can see it's automatically loading standard IO.H. And now we're in the editor. So the first part of this header file is all of these number sign defines. These are called macros. And what it says is anytime you see this phrase, replace it with this when you run it through the C compiler. So this gives us some nifty, easy to remember shortcuts versus the numbers that are on the right side. For example, the word null is a 0. CR, which is usually a carriage return, is \n. Now, one thing that's kind of interesting is look at the constant for CLR. This is the clear key to clear the screen. If you're familiar with Commodore Basic, that's usually CHR$147, but here you see 223. You might be thinking, that's kind of strange. What weird character chart are they using? Well, they're not. These numbers are in base 8 octal. Yep, one of the few times you'll ever run into base 8 in the wild, I think. So that 223 is base 8 for 147. Now if we scroll down a little bit more, so in this section we see the word extern in front of what looks like a bunch of function declarations. This is how we kind of create a link between standard IO.H and libc.l. When you have the word extern, when the compiler sees it, it knows that the source code is not in this file, but instead it's compiled in an object link file, and the linker will handle the linkage to it later on. Here's some more definitions, and here is source code for a function called getCar. And if you remember back when we compiled the code, we saw getCar in yellow, meaning the source code for inside the header file. So here you can see the function getCar, and it goes into an endless loop and waits for a character to be pressed. And then when it finds it, it returns it. So header files can also contain source code, not just definitions and not just external function pointers. In fact, they are treated as full source code files that are inserted into your source code. So when you see a .h and a .c file, to the compiler, they're really the same thing. So this file has actually got a lot of really useful information in it. It would be really nice if we can keep this in memory for reference, and we can. There's a special area in memory called the extra text area. If you press the home key, it'll bring you to another text editing window that you can store extra text in. If you press the home key, it brings you back to the source file that you're editing. So if we press F5, we can transfer the contents of this editor to the extra text area. And we do that with the T key, which is transfer. And then you just use a cursor key to highlight what parts you want to bring over. Maybe we'll bring over, I don't know, everything. We press enter, and now it's going to say fixing target, meaning where do you want to put it. This is a way to copy and paste within a file, but we're going to press home, go to our extra text window and press enter and put a copy here. Now we can press home and go back to the editor where STDIO.H is. All right, so let's load our hello world file in. So we're going to do F5, L for load, hello world.c. So let's create another function for our program. And we're going to press the F7 key a couple times to give us some space above the main function. And we're going to create a new function called initScreen. So we'll just do void initScreen. And again, to do the curly braces, you press, if you're in Vice, of course, you press caps lock to put the shift lock key on. You press shift plus, turn the scroll lock off. We'll hit enter a couple times. Turn the caps lock key back on, and then press minus. Turn caps lock off. Kind of a pain in the butt, but it works. I'll hit the tab key to indent. So the purpose of this function is to clear the screen. And we're going to do that by using the printf function, which we were introduced before, except now we're going to introduce some formatting constants to it. The way printf works is it not only prints the text in between the quotes, but if you use these percent commands, so we'll put %c, it means that this is a placeholder for a character. So we'll put a quote, and then after that, you put a comma limited list to fill your placeholders in. And we're going to do CLR, close parentheses, semicolon. So if you remember a few moments ago, and I'll press the home key to show it to you now, CLR is going to put in, with the quotes here, single quote, backslash 223 backslash, which again is octal for 147, or clearing the screen. So we can press our home key to go back to our source code. So it's really nice having that little text edit area, so we can use it for a whole variety of things, like having a header file that we want to kind of look at, or you can load the last compilation error text file there so you can compare it to your source code. Now we're going to interact with the VIC chip of all things. One of the nice things about C is you're really just a nice structured language layer above assembly language. So we're going to interact with Commodore 64 in a pretty direct way, which C is great for. So we're going to insert a line or two above our printf command. And what we want to do is we want to change the border color to a different color. And we even change the screen color as well. And we do that through what's called pointers. Pointers in C are cool. For a lot of programmers, it's like they're a big stumbling block for learning C. So I'm going to teach you just a really, really simple pointer just to kind of get you started, and then maybe we'll get deeper into it later. One of the types in C is a char, a character. And a character in C, or in Super-C, can contain a single character, you know, like an A, a B, a C, or a number between 0 and 255, representing a byte in memory. However, we can create what's called a character pointer. You do that by putting a star in front of it. So now what this represents is a memory address that can contain a character. On the Commodore 64, all memory addresses can contain one 8-bit value or a character. So with this here, we've declared a variable called C that is a character pointer. So what we need to do now is assign it a memory address where we might want to put a value in. And we can just use a number like, say, 53280. And 53280 is the memory address where the VIC chip uses to control the border color of the screen. You can also use hex if you wanted to. If you were going to use hex, you would use 0xD020. 0x means that the next 4 digits is going to be a hexadecimal number. We'll leave it as 53280. So if you're coming from BASIC, this will feel at home. So as you can see, when we use the letter C by itself with an equal sign, we're assigning a memory address to the pointer. Now, how do we do the opposite where we assign a value to the memory address that the pointer is pointing at? Well, we're going to use the asterisk operator again, except this time it behaves differently than it does when you declare a type. And we're going to say asterisk C equals 2. This will put the value of 2 in memory address 53280. When we use the asterisk on this line, it's called dereferencing the pointer. I like to think of it as poke. So if you're coming from BASIC, this I would read as poke C with 2. Or C is the memory address 53280. Pointers are difficult. A lot of people, it's a big stumbling block in the language. This is, I think, is a really simple way to start. We can change its memory address by just using math. So we could say C equals C plus 1 to add 1 to the pointer, bringing the memory address to 53281. In C, there's a shortcut for adding 1 to a value, and you just type in C++. That'll increase the number of C by 1, so 53280 becomes 53281. And then once again, we can use *C to poke a value or dereference the pointer and then store a value in its address. And for this one, we'll use, 1. That should make the screen white. So now that we have our function, we need to call this function. So we're going to come down to our main function here and insert a line above, and we're just going to type in init screen semicolon. All right, so let's try to compile this. So first we want to save it. We're going to press F5, we're going to press S. Because the file exists this time, it's going to ask us if we want to replace it, so we'll choose yes. All right, we're going to press F5 again and X to exit out of the editor. So when we compiled this earlier, we ran CC and it asked us a bunch of questions. We could actually kind of anticipate the questions and feed it to him on a command line, making this process a little bit more efficient. So we can type in hello world.c, because the first thing it asks us is what's the source code file we're creating. The second thing it asks us is what object file we're going to create, and that's hello world.o. And the last thing it asks us is the name of the text file that it's going to create if there's any compilation errors. So doing this, we no longer have to interact with the program. So at this point, the program's going to load, it'll pre-fill those values in, and let us know what the results are. With C64 being as slow as it is, this is one of those things that really helps a lot, because you can go up, get yourself a cup of coffee, mow your lawn while this thing loads, whatever it is, come back and see how it worked. And here you can see that it pre-filled our questions for us, and now it's going through the compilation phase. Notice here how the function is called init-scre, or in our program it's called init-screen. The C compiler in Super-C only recognizes 8 character function names, so just be careful if your functions have the first same 8 characters. The compilation finished successfully, a link file is available, we can press X to quit. Now the linker can do the same thing. We can anticipate some of the questions that the linker asks us. So we can call the linker with CL, right? We know the program we want to create is called Hello World. It's going to ask us for the libraries, and we know that libc.l is the standard C library. Our hello world.o is the object file that we want to link it to. Now, when you run it this way, you don't get an option of BASIC or CCP. It will always create it for the CCP. And again, that's okay for what we're doing. So we'll just let it link to a CCP program. It also does not let you override the top page option. And that's okay again. 9 times out of 10, this is how we want to link our program. Our linking is finished. We're going to press X to quit. And now let's run our program and see how it worked. hello world. And there we go. We have a red border, a white foreground color, and our default gray text that was inherited from the CCP. It's waiting for a key. We can press the key, and then it brings us back to the CCP. So passing in the command line arguments to the C compiler and the C linker does make the process a little bit more efficient. They do give you another program called C1 that makes the process very efficient. And you invoke it by typing in B:/C1 space and the name of the executable that we want to create, which is hello world. This program takes a look at the word hello world and first calls the C compiler with hello world.c. Instead of hello world.o, it passes o.o for the object file name, which is fine, and it passes error.e. So it'll automatically run the C compiler and do all that typing for you. If that process is successful, it will continue on and call the linker and pass in the appropriate parameters. Now that the process is finished, we just press X to quit. And now we've recompiled our Hello World app with a much more efficient process. So let's take a look at some of the demo software that comes on a disk. So if we type dir spr star, we can see that there's a program here called SPR Demo. And this is a demo that shows how to create and use sprites in C. So to get started, we're going to put a blank disk in drive 8, and we're going to format it for this Sprite Demo project. And we'll start by formatting that disk. So do a:/com:/n: Sprite Demo. And we'll just let this disk format real quick. Then let's start copying the required files that we need to build this demo. So we know right away we obviously want sprdemo.c. That's pretty straightforward. Oops, almost forgot to put a b: in front of that. This way you could find the file on that second disk. And we're going to want a copy of this sprlib.l, so we'll bring that down as well. And the two files that every program needs is STDIO.H and libc.l. So let's take a look at sprdemo.c's source code and just make sure there's no other files that we need that aren't obvious from just the file names that we see on the disk. So here's the source code, and there's a nice little comment at the beginning about this is a demo of how you can call sprites in Super-C 64. This should also give you an idea of how to access a SID chip and other stuff. Enhance, enjoy, and remember, you'll also need to download sprlib.l, and vic.h. There's the other file that we need, so we just need to be aware of that. Now, what I do find interesting in the source code, right in the very beginning, is that it's including a .l file. And if you remember correctly before, we said .l files are object link libraries. They're binary files. So I suspect that this is source code masquerading as a library file. We'll come back to that in a moment. Let's take a quick look at the program. This looks like sprite data, 63 bytes of data to create a sprite. And then here's the main function, and this program is pretty short. I'm not too familiar with this library, but it looks like it sets the definition up. It's talking about, I'm assuming, the VIC chip in block 3. This code is clearing the screen. Set the sprite color. I'm assuming this turns the sprite on or configures it in some way. And then here's an infinite loop, or it's just moving the sprite. And yep, that's the whole program. Let's address this particular problem here, sprlib.l. Since we're pretty confident that this is a source code file, we're going to want to rename this .h. I don't like having .l files not being real library files. So we're going to save this here, and we'll replace that file. Then let's exit out of here, and let's rename that file. So we'll do a:/dir, and we're going to use that com command again, except we're going to do the rename command. That's r:, and what you say is the new file name, right? So it's going to be sprlib.h equals sprlib.l. And let's rename that. Excellent. And it did say in the comments of that file that we need something called vic.h. So let's see, is there a vic.h on this disk? And there is. So let's copy that. Oops. My instinct for DOS kicked in. I forgot to put the asterisk here. There we go. So at this point, I'm pretty confident we have all the files on a disk that we need. So we're going to use this C1 program to compile it. So we'll just do C1 SPR demo. And if we got everything on a disk, this should compile it and then pass it off to the linker and link it. All right, we're going to press X to exit, and let's take a look at this Sprite demo. And we run it by a:/SPR demo. And there it is. There's a sprite, and it's just kind of flying across the screen. I'm assuming that's supposed to be a spaceship, I hope. But pretty neat. So that's the Sprite demo, and as you saw, it's just about a page and a half of code to get that going. So that's pretty impressive. So let's exit out of here. When we looked at the source code, it was an endless loop, so we have to run, stop, restore to get out of this program. And then we'll get that NMI interrupt, press X to quit. And we're back at the Super-C command processor prompt. So on a disk, there's a program called cdemo.c. And this is like the super demo. It's basically a product demonstration meant to be run maybe in a store or something like that. So it's kind of a really cool one. So I put a blank disk in drive 8, and let's format that so we can build and compile and link this demo. So we'll do a new drive, cdemo, CZ, and we'll just give this a couple seconds to format. All right, and then we're going to copy cdemo.c to the A drive. And as you can see, this program is a monster at 101 blocks of source code. Oops, forgot to put the B colon in the file name. All right, then we'll just copy the usual suspects over, which would be STDIO.H. Oops, almost got that B colon again. There we go. All right, we're going to need libc.l, of course. All right, we're actually going to need the graphics library for this. So we're going to pull down graphic.h. and libgraph.l. Let's take a look at the C editor and take a look at the source code for this before we build it. So before we load the source code, if we press F5 and B, it tells you how much memory is left remaining for source code. We have about 44K. So let's load this file in, cdemo.c. So if we press F5 and B again, we can see that there's still 19K left. So even after loading this mammoth source code file, there's still a ton of room in memory to create C source code. So that is pretty impressive. So this is kind of interesting. It talked about how they're kind of sorry that this program was translated, and there's a couple comments and variables in German, which I think is kind of cool. So here's the two includes that we talked about, standard IO and graphic.h. And if I press the F1 key, it's like page forward, you can kind of get an idea of just how big this program is. It just kind of goes on. There's just a lot there. And if we get down to the bottom, we're about 1,200 lines in. I'm going to make one small change to this program. There's something I didn't like about it. There's a part, which you'll see when we run it, where it shows a clock and it waits. And it waits, I think, too long. This first parameter to their clock function is how many seconds before it moves on to the next demo. I think 15 seconds is about all I could tolerate waiting. Some of these are like 2-3 minutes. It just takes way too long. So there we go. We've made our clock go a little quicker. All right, so we're just going to save this. All right, and we're going to exit out of here. And we're just going to take a quick review of the disk before we build it. So 101 block source code file, our 2 header files, and the 2 libraries that match those header files. So normally I would just run the C1 command and build it. I mean, up to this point, I have edited out like 95% of the load, compile, and link times. And so it makes the product look like it's really fast. But believe me when I tell you, it is glacial to use this product. So what I'm going to do is, instead of building it like normal, I'm going to build it with a clock running on it so you can see how fast it builds. But I'm actually going to do 2 things here. I'm going to build it with 2 windows. You'll see 2 windows side by side in a moment. You're going to see what this is, like a stock Commodore 64 building it on one side. And then on the other side, I have an emulator running the JiffyDOS ROMs. So you can see how much faster JiffyDOS has. So if you're going to be working on an actual Commodore 64 with this C compiler, which by the way sounds super fun, you're going to see how much impact something like JiffyDOS would have on the development experience. So here we go. Wow, that is impressive. JiffyDOS is almost twice as fast as a stock 1541 disk drives. But yeah, you could see if you had JiffyDOS, developing on your Commodore 64 was almost twice as fast. So that's a pretty huge impact. All right, let's go take a look at this demo. All right, now that we have the demo build, let's give it a run. So the demo starts by asking you for the time, and this is for its analog clock. So we'll just put in, I don't know, 12:30:00. So the demo starts by showing the capabilities of the high-res graphics library. And you can see it's just basic lines and fills and things like that. An interesting fact about the high-res color mode that's available to you through their library is that it's in multicolor mode, so it's 160 by 200, but you can only choose 4 colors as opposed to 16, which is usually available in high-res color mode. The included demo does not have any sound or music in it, which I find interesting. There is reference to sound in the graphics library and the JiffyDOS.H header file, so it might be an interesting project to go back and see what kind of sound routines we can create for this. So in this slide, they're going to talk about the CCP and the commands for managing the disk drive along with the 24-hour clock, and we did play around with that a little bit in the beginning of the video. This slide talks about all the commands that we've been using in this video, the editor, the compiler, the linker, and of course the libraries that come with it, the graphics, the math, and the standard library. In this slide, they're showing an example of the high-res graphics routines by making an animated analog clock. You can see the 4-color limitation here. So I did play around with the 128 version as well, and it's quite different than the 64 version in 2 major ways. The no good ways is they give you a drive H that's a RAM drive that has 64K or 240 blocks. It mentions in the manual that they're going to add support for the 256K REUs, but I don't see any evidence that that feature exists in the product. I could not get it to work on my 120 emulator. Also, the 128 version does not allow you to compile to BASIC. You can only compile to CCP. So if you want to redistribute your programs outside of the 128, you can't really do it with the 128 version, which is kind of a letdown. Perhaps I'll cover the 128 version in more detail in a future video. I'm not quite sure if there's interest in it, but if there is, let me know, and I'll definitely take a closer look. And of course, the 80 comp support in the 128 version is actually super nice. Here's another slide showing the graphics capability of the included graphics library. Unfortunately, once again, you can see that 4-color limitation, and it reminds me of CGA graphics from the early PC era. Given that we have full access to the VIC chip and everything in the Commodore, I wonder if it's possible to add 16-color support ourselves. Might be an interesting thing to explore. And this slide just shows you how fast the library can calculate prime numbers up to 10,000. Kind of neat. And at the end, it shows you how fast it ran compared to BASIC. And this concludes our tour of the Abacus Super-C package. I hope you had as much fun watching as I had putting this together. And somehow we hit 3,000 subscribers, which is insane. So thank you everyone for watching. I truly appreciate it. So if you have any ideas of programming languages or just obscure software packages or databases or anything you'd like to see me explore, please let me know in the comment section. And until then, thank you all. Take care.